Good morning, y'all. No fancy lighting or anything like that, so I'm hoping that the lighting isn't too crazy on this. It's just the light of the room. But anyway, I'm going to go ahead and solve each one of the Chapter 2 test review problems. And I'm going to do these videos in increments, so hopefully they upload faster. So I'm going to do it page by page. So the first page is problems 1 through 6. So let's get started. Okay, and number 1. Suppose that f of x equals root x. Calculate the average rate of change between 9 and 9.1. Do the same for 8.9 to 9.0. And then use those answers to approximate the instantaneous rate of change at x is equal to 9. Okay, so what I know is that f of x is equal to root x. And this is definitely a calculator problem, so I have my calculator handy. And in part A, we want to find the average rate of change between 9 and 9.1. So x equals 9 to 9.1, so that's the interval I'm working in. Well, we know that the average rate of change is equal to f of b minus f of a over b minus a, right? And this is always a and b, so alphabetically. So f of b is f of 9.1 minus f of 9 over 9.1 minus 9. And f of 9.1 is just root 9.1. F of 9 is minus root 9 over 0.1, right? So the idea is, I evaluate f of 9.1 and I evaluate f of 9, and then I plug it into that little formula. And I don't know what the square root of 9.1 is. It's 3 point something. So I'm going to leave it like that. I know the square root of 9 is 3 over 0.1, or a tenth. And now I'm going to use my calculator to get an approximation. So I have square root of 9.1 minus 3, and then I have to divide that by 0.1, and what I get is about 0.166. So in AP, we round to 3 places past the decimal, or we go 4 places past the decimal. So I'm just going to go to 3. And that's the average rate of change of this function f between 9 and 9.1. In B, our interval has changed. It's going from 8.9 to 9. Okay, again, why this thing keeps, sorry, I must have hit it or something. Let me refocus. Keep in mind that in this case, 9 is the leftmost endpoint of this interval, and over here, 9 is the rightmost endpoint. So it makes sense that in part C, we're going to estimate the instantaneous rate of change at 9. Okay? Anyhow, we're going to go through the same thing. We have that the average rate of change is equal to f of 9 minus f of 8.9 all over 9 minus 8.9. And f of 9 is root 9 minus root 8.9 over 9 minus 8.9 is 0.1 again. So now we have 3 minus root 8.9 over 0.1, and time for me to get out my calculator. Move this over here. So I've got 3 minus root 8.9 divided by 0.1 is 0.167. This is 0.167. So this is part A. That's the answer to part A. This is the answer to part B. And by the way, since I have to estimate the instantaneous velocity in part C, technically speaking, you should go out on these answers further, because I'm probably going to have a rounding error, right? And even if it's a small rounding error, you know, on the AP exam, they're going to have a particular value and that they're looking for, and if you make a rounding error, you're going to get it wrong. So just keep that in mind. I'm being a little bit sloppy here for the sake of saving time and because I hate writing decimals, but but you should bring those numbers out and round at the very last minute, okay? So in part C, it says use your answers in part A and B to approximate the instantaneous rate of change. Well, we know that the instantaneous rate of change is just going to be the average of the average rates of change. So in other words, it's 0.166 plus 0.167 divided by 2. And if I'm going to leave this one out here like that so I can get it a more accurate, plus 0.166. I'm leaving this last answer in its long form, and I'm going to add to it part of the answer from the other one. So I get about 0.333. So the instantaneous rate of change is estimated to be about 0.333. And that's it. That little square just means I'm finished. Okay? In math we use that to mean we're done with the problem. So you can use it or not use it, it doesn't matter either way. Right, so that was number 1. Number 2, the dropping ball. Okay, so number 2, we've got a ball dropped from a height of 400 feet, and it falls toward the earth in a straight line. In t seconds, the ball drops a distance of d equals to 16 t squared feet. How many seconds after release does the ball hit the ground? Okay, so the idea here is that the ball is already 400 feet above the ground somewhere. Maybe it's on a shelf or something, or a ledge. And so here's the ball on some thing, maybe. And the distance, okay, that the ball drops, so the distance here, or it's going to fall here, the distance that it drops is going to be represented by the 16 t squared feet. So what we want to do is, in part A, figure out how many seconds it's going to take for the ball to hit the ground. So, you know, all you have to do is say 16 t squared is equal to 400, right? And if I divide both sides by 16, I get t squared is equal to 25. Time cannot be negative, so I know that t has to equal 5 seconds. So it takes 5 seconds for the ball to hit the ground. Okay, B, so that was A. B, what is the average velocity of the ball during the time it's falling? Well, the time it's falling is an interval from 0 to 5 seconds. So f of 5 minus f of 0 over 5 minus 0 is going to be equal to the average velocity, right? F of b, dang this thing, f of b minus f of a over b minus a. So I have to say to myself, what is f of 5? Well, if I'm just working on the function, right, so my function is 16t squared. You can call it f if you want, doesn't matter. This is the function. So if I evaluate this thing at 5, 25 times 16 is 400. So you have 400. F of 0 is 0. 5 minus 0 is 5. And so if I do 400 divided by 5, I get 80 feet per second. Okay, so the average velocity for the time that the ball is falling is about 80 feet per second. And in C, we want to estimate the instantaneous velocity of the ball when it hits the ground. Now, I've heard a lot of you say, well, it must be 0, right, because it hit the ground. but it's not true, because at that instant it hits the ground, it has some particular velocity, and then it's going to bounce back up again, right? So it doesn't just like stop, or the velocity doesn't just go necessarily to zero. I don't know, maybe if it's like a lead ball or something, but we're not talking about a lead ball, we're talking about like a tennis ball or something that bounces, okay? So we know that the ball hits the ground at t equals to 5, right? We know it hits the ground at t equals to 5 seconds, okay? So what we want to do is, the best way we can estimate this instantaneous velocity is take a point a little bit to the left of 5 and a little bit to the right of 5. So think of a number line, right? Here's 5. If I go a little teeny tiny bit to the left, we'll say 4.9, right? If I go a little teeny tiny bit to the right, I have 5.1. I don't know why this thing keeps doing this. Maybe it's too early in the morning for this Elmo. Sorry about that. And find the slope of the secant line and take the average. So, if I'm working on this interval first, I might do f of 5 minus f of 4.9 all over 5 minus 4.9. And if I do that, I'm going to put that into my calculator real quick. Well, actually I'm not. And also I'm going to do this interval here, right? So f of 5.1 minus f of 5 all over 5.1 minus 5. Okay. Now f of 5 means I have to plug 5 into my function, right? 25 times 16, so that's 400. And I have to plug 4.9 into that. So 4.9 squared times 16. Oops, 4.9 squared times 16. So that's like 384.16 divided by 0.1, right? 5 minus 4.9. And over here on this side, I've got to do f of 5.1. So 16 times 5.1 squared is like 416. 16 minus 400, again over 0.1. Okay, so I'm just computing the average velocity here, the average velocity here. I'm going to find out what those results are, and I'm going to divide by 2, and that's going to give me the best approximation of instantaneous velocity that I could ever hope for given the circumstance. So we've got 400 minus 384.16. So this becomes 15.84 divided by 0.1. And over here, 416.16 minus 400 is going to give me 16.16 over 0.1. Now this is just, 0.1 is 1/10. So in other words, if I multiplied the top by 10, it's just going to move my decimal. If you're not familiar with that, well, you can use your calculator. You can divide by 0.1 and you'll see the decimal move. So here we're going to have 158.4 roughly, and over here we're going to have 161.6. And so now if I add those together and divide by 2, I'm going to get 160. So, and that would be in, what are the feet per second, right? Feet per second. So, I don't know if that's what the answer is. I have the key here. Let me just look. Yeah, perfect. I got it right. So, anyway, that's how you deal with something like that. And you figure out, or you determine a little number to the left that's really, really close to, the number in question, the time that it hit the ball was at 5. And then choose a number a little bit to the right, and then use those to find those average velocities and sum them up and divide by 2 to get the instantaneous velocity. Okay, so number 2 is fini, done. I'm seeing shadows in the video. See the shadows? Hi guys! It's irritating me. And it's only 6:04 a.m. Okay, number 3. Number 3, we have a table. So I'm going to put this here. And we've got an object traveling. And its position at various points is given in this table. And for part A, we want to find the average velocity of the object between t equals 1.3 and 1.9. So, you know, this 1.3 and 1.9. That's my interval. X goes from 1.3 to 1.9, right? So, the idea is if I'm looking for average velocity, I know that average velocity is going to equal to f of 1.9 minus f of 1.3 over 1.9 minus 1.3, right? This is A, this is B. So, you know, if that bothers some of you, let me just write it this way. The interval in the x values goes from 1.3 to 1.9. So this is A, this is B. So it's f of B minus f of A over B minus A, right? So, again, let me just rewrite this because I need more room anyway. 1.9 minus f of 1.3 over 1.9 minus 1.3. Well, f of 1.9, if you look back in the table, the function evaluated when x is 1.9 is 53. So we have 53 minus the function evaluated when x is 1.3 is 5.1. Oh, it's 5.3, not 53. 5.1. And then it's going to be 1.9 minus 0.3, which is 0.6, right? And 5.3 minus 5.1 is 0.2 divided by 0.6, or 2/10 divided by 6/10, right? And so anyway, we get about 0.333. That's the average velocity over that particular interval. And now, this was a mistake on the part of George Best. He wanted you to estimate the instantaneous velocity at t is equal to 1.9. And if you look at the answer key, so just in case you don't have that handy, I want to make this clear. What number is this? 4? Oh, yeah, B, 3B. If you look at the answer key in 3B, it's very clear. He wants you to estimate the instantaneous velocity at 1.9, and there's no way you can do that. If you look at the values in the table and then what he's using in the answer key, he's using 5.7 and 5.4. So he clearly wants the instantaneous velocity at 1.5. So he made a typo there. I don't make these. George Best does, and I thank him for it. Okay, so really what he's asking you for is the instantaneous velocity here. Now look, I can use these 2 points and find the slope of the secant. And then I can use those 2 points and find the slope of the secant. Remember, this is what I'm after. What's the instantaneous velocity at that point? But I don't want to do that because it's too much work. Rather than that, I can say, well, you know, this is the interval that I'm working in. Make sure you put that point in question right in the middle, and then have 2 endpoints, and then you can just do f of 1.6 minus f of 1.4 over 1.6 minus 1.4, and that's going to give you the same answer. So let's do that. So in 3B, so 3B, we're going to have f of 1.6 minus f of 1.4 over 1.6 minus 1.4. That's a point. F of 1.6 is 5.7 minus 5.2. 1.6 minus 1.4 is 0.2. And if I pop that into my calculator, because I don't want to make an error, because I have not had enough coffee yet this morning, we get 2.5. And guess what? He did it the long way in the answer key. Okay, just to show you. You know, he took the average from the left, the average from the right, he added them together, he divided by 2, and he got the same exact answer. So you can be more efficient and do less work by just making sure that that point in question, or that point that, you know, you're being asked about, is sort of nestled in the middle between two other points, and use that whole thing as your interval and just use f of b minus f of a. Makes life much easier on the problem solver. Alright, I'm with this paper. Let's look at number 4. Number 4, they tell you the average rate of change from 1 to 9 is 3. And f of 1 is fine, so find f of 9. So I did this in class, but I'm going to do it again, because I said I would, and maybe not everybody was paying attention because they were working on something else. So, my interval, so this is number 4, my interval is 1 to 9. So I just write it down like that. Okay, and I'm really sorry about this Elmo thing. I don't know what's going on with it. I really apologize for that, but it has a mind of its own. So there's our interval, and we are told that the average rate of change over that interval is 3. And we're also told that f of 1 equals 5, and we want to find f of 9. Okay. We know that the average rate of change of a function is f of b minus f of a over b minus a, right? The non-sophisticated way of writing it, the slope of a secant line. And what we also know, because we were told, is that the average rate of change is equal to 3. So I'm going to plug a 3 in to the left-hand side of this equation. And so a is 1 and b is 9, so f of 9 minus f of 1 over 9 minus 1. Simplifying this a little bit, I have no idea what f of 9 is, but I do know that f of 1 is 5 because they gave that to me. So I've simplified this a little bit more. And now I'm going to solve for f of 9 and I'll have my answer. So if I multiply both sides by 8, I'm going to have 24 is equal to f of 9 minus 5. And if I add 5 to both sides, I'm going to have f of 9 is equal to 29. Done. And number 5, it says let g of x be equal to x squared plus 5x. In part A, they want you to find the average rate of change on the interval from a to a plus h. Now that may seem weird, but don't let it bother you. It's just an interval with a and a plus h in it. Okay, well, if we want the average rate of change, we know that the average rate of change is equal to g of b minus g of a over b minus a, right? This is an interval from a to b. Okay, well, what's g of b? G of a plus h is what they're asking me for, so let me just do a computation. That's equal to a plus h squared plus 5 times a plus h. There are no numbers in here, and it's okay. I'm going to get an expression. So expanding this, I'm going to have a squared plus 2ah plus h squared plus 5a plus 5h. And it doesn't look like I can combine anything. So that's my g of a plus h, or my g of b. G of a means I plug an a in for g, or for x rather, in the function g of x. So I'm going to have a squared plus 5a. That's my g of a. So, using the formula, I'm going to have a squared plus 2ah plus h squared plus 5a plus 5h long minus g of a. So I'm putting parentheses so I don't forget to distribute properly all over h, right? And now if I distribute these signs, I'm going to have a squared plus 2ah plus h squared plus 5a plus 5h minus a squared minus 5a all over h. And let me get a color. And what you notice is the a squareds are going to go away and the 5a's are going to go away. Right? So we can simplify this a little bit more. We've got 2ah plus h squared plus 5h over h. And in part A anyway, they just want that average rate of change, and we have to simplify. Ooh, we have to simplify. So that means I can factor out an h. So let's do that. If I factor out an h, I have 2a plus h plus 5 all over h. Those cancel. So I have 2a plus h plus 5. That's my average rate of change from a to a plus h of this function. And that's it. In part B, they want us to find a formula for the derivative. Well, look, you already got, the formula for the derivative is the limit as h approaches 0 of g of a plus h minus g of a all over h, right? We know this. So what you've done up here is you've taken care of this part already. So the formula for the derivative, g prime of a, is equal to the limit as h approaches 0 of this thing right here, this thing, of 2a plus h plus 5. So all you've done was the hard part of that work. Now it's simplified, so at this point you just have to plug the 0 in. So the derivative is 2a plus 5. Done. Nice stuff. In number 6, there was some confusion. I think I clarified it for some in class, but let's fix this. This really is just to test your understanding of what's going on. So in number 6, so this will be the last problem for this video, it says on the graph, sketch a line whose slope is f of 4 minus f of 1. Well, that means you just have to plot points on the graph. The interval goes from 1 to 4, right? This is the change in x here, the domain. So, you know, when x is 1, y is something. And when x is 4, f of 4 is negative 1 or something like that. And get my straight edge. I'm all prepared this morning. There's my line. It says label it line 1. So I did that. That's all they're asking you to do. And then in part B, it says on the given graph, now sketch a line whose slope is. So you see, this is what is the slope of the tangent line when of this function when x equals to 3. So you get another color, and that means, all that means is I'm going to go to the point where x is equal to 3, and I touch the graph with a point, and I'm going to draw the best darn tangent line I can come up with, and I'm going to call it L2, and that's it. You tell I like purple. So that's all you had to do for number 6. I hope this helped, and you'll see the subsequent pages, or the following pages, coming along real soon.